Swayam Prabha. Digital India. Educated India.
So, let us start working. First question we ask is this: what is the number of classes? Y3? There are 4 classes, right? E, C2, sigma V dashed. 4 classes. So, there are going to be 4 irreducible representations. So, all this time the question that we have been asking, that is answered in a second. We are going to have 4 irreducible representations for C2v. Fine. So, to start with, let us name them gamma 1, gamma 2, gamma 3, gamma 4. Okay. 4 classes, this gamma 1, gamma 2, gamma 3, gamma 4. Lines are just guides to the eye. What next? The next question to ask is, what are the dimensionalities of these 4 irreducible representations? And this is what will give me the answer. Sum over I, Li square equal to H. What is H? H is 4, right? So, L1 square plus L2 square plus L3 square plus L4 square equal to 4. Can L be a fraction? Can you have a 3/5 by 3/5 matrix? Okay. Can you have a minus 20 by minus 20 matrix? No. So, Li has to be a positive integer, right? It has to be a positive integer. So, now see, L1 square plus L2 square plus L3 square plus L4 square is equal to 4. What will be the values of L1, L2, L3, L4? All have to be equal to 1, right? So, Li equal to 1 for I equal to 1 to 4. That means for C2v, you have a total of 4 one-dimensional irreducible representations, right? What is the next job? I want to fill in, I want to know what the characters are, and to do that we are going to start with, we are going to use this chi I r square equal to H. In fact, we do not even have to go that far to start with. Can you fill in one of the columns? The first column is not very difficult to fill, right? Yes. If you remember, chi I e is equal to Li. Li is 1 in all these cases. So, I can write the first column very easily, 1, 1, 1, 1. Okay? And I can write the first row also. The first row is always 1, 1, 1, 1, as many number of ones that you have to write, because that would stand for something that is totally symmetric. What is the meaning of 1 here? No matter which symmetry operation you perform, your basis remains unchanged. That is the meaning of character of 1, right? Yes? Oh, how come you noticed it from there? I didn't notice it from 1 foot away. Huh. Okay, so first row is always all ones. That is called the totally symmetric representation. No matter what you do, there is no change. That will be there for all symmetry point groups. Now we have to fill in the rest. How do I fill in the rest? Okay, we start with sum over r chi I r square equal to H. What is H? So, the thing is this, these are all one dimensional representations, you told me, right? So, will you agree with me that all characters have to be either plus 1 or minus 1? Why? What is the meaning of plus 1? It does not change, symmetric, right? What is the meaning of minus 1? Antisymmetric, changes sign. What would be the meaning of 0? Suppose I have one dimensional representation with character 0. What would it mean? One dimensional representation. One dimensional representation, character 0 would mean annihilation. Right? It would mean annihilation. You perform a symmetry operation and your basis vanishes. Not going from one basis to another basis, going from a basis to no basis. Annihilation. Annihilation is definitely not a symmetry operation. Right? Annihilation is as non-symmetry as it gets. So 0 cannot be there. What about 5? Can I have a character of say 5 in a one dimensional representation? Let us see. Let us say I have some basis x and I have some symmetry operation R whose character in the one dimensional representation is 5. Now when the symmetry operation operates on x, what does x become? 5 times x, 5x, right? What is that? If I hold you and somehow stretch you, then you are not going to call it scaling anymore, you are going to call it distortion, right? So this is distortion. If it is just multiplied by some number that is not 1, then it is distortion. Distortion once again is not a symmetry operation. So it cannot be anything other than +1 or -1. Since all the representations are one dimensional, the only characters you can have are +1 and -1. Alright, but how many +1s, how many -1s? The answer comes from here. Sum over R, chi I R, chi j R equal to 0. What does that mean? I know one representation anyway, 1, 1, 1, 1. Now let us say this is A, this is B, this is C. So now 1 into 1 plus 1 into B plus 1 into, no sorry, 1 into 1 plus, better write here. 1, 1, 1, 1. First one is 1 anyway. I will call this A, B and C. So 1 into 1 plus A plus B plus C, that should be equal to 0. And all are either +1s or -1. What does that mean? Out of A, B and C, 2 have to be -1, 1 has to be +1. Okay. Now knowing that, what you do is you fill in the different places by the -1s and +1s, right? There are 3 places and 2 -1s. 3 places have to be filled with 2 -1, 1 +1. How many possible combinations are there? 3. And how many vacancies are there? 1, 2, 3, right? So it's good. LHS equal to RHS, as we always want it to be, no problem with that. You fill in 2 -1 and 1 +1. So in all, in every representation you should have 2 +1s and 2 -1s. So this is what you get. 1, 1, -1, -1, 1 -1, 1 -1, 1 -1, -1, 1. Question? Yes. We don't. To start with, at this point we don't. You would be perfectly right to write 1 -1 -1 1 first. But as we will see, we are not going to leave these representations named so generically gamma 1, gamma 2, gamma 3, gamma 4. We are going to give them some names, and when we give them some names, we like to arrange them by those names as well. That is why, as always, I have the benefit of hindsight. But to start with, if you work this out and if you write it in a scrambled order, I am fine. Okay, are we okay? Can we go ahead? Can we go ahead? Okay, good. So now let us see the basis. What fits in where? let us start with x, y and z. Let's start with z. Where will z fit? If you perform E on z, character is 1. If you perform C2 and you consider C2 to be the z axis, character is 1. Sigma v, what is sigma v? Zx, character is 1. What is sigma v dashed? Yz, character is 1. Alright, 1, 1, 1, 1. So that is where z belongs, to gamma 1. Z is totally symmetric with respect to all the symmetry operations of C2v. Now, do you think that is the case everywhere? Can I have some symmetry species? No. Can I have some point group where Z is not going to be totally symmetric? Anything that has a sigma h, right? This is Z axis. This is what sigma h would be. So, for reflection with respect to sigma h, plus z would become minus z would become plus z. So, whenever there is horizontal plane of symmetry, z would definitely not be totally symmetric. Okay, fine. What about x and what about y? Consider sigma v to be zx and sigma v dash to be zy. This is conventionally taken to be zx. First one is x, after all x comes before y in the alphabet. So, sigma v zx, sigma v dash is yz. Right? Symmetric with respect to sigma v. So, x is in the zx plane, so it has to be symmetric with respect to sigma v, whereas y is perpendicular to it, so it has to be antisymmetric with respect to sigma v. And the same logic holds for sigma v dash. The behavior of x and y are just the opposite because the plane is now yz instead of zx. Fine, simple. Okay. Now, what about x square? Where will it belong? X square, suppose I take x square. Where will x square belong? X square is always positive, right? It has to belong here, gamma 1. It cannot change sign, isn't it? X square cannot change sign. Y square will also belong there and z square will of course belong there. That is not the case everywhere. It is the case here, but that is not the case everywhere. Okay. So, all the square terms will belong here. What about xy? Okay, what you could do is you could just multiply the characters and see what symmetry species you get. Okay, xy, that means this and this. You multiply gamma 3 with gamma 4, what do you get? 1 multiplied by 1 is 1, minus 1 multiplied by minus 1 is minus 1, plus 1, good. Just checking if everybody is awake and attending. 1 multiplied by minus 1 is minus 1, minus 1 multiplied by plus 1 is minus 1. So, we have 1, 1, minus 1, minus 1, gamma 2. So, that is where xy should belong. Then you tell me where yz should belong. See, the nice thing about z is that all characters are 1. What is easier than multiplying by 1s? So, yz will belong in this case to the same irreducible representation as y, and zx will also belong to the same symmetry species as x. Alright? Okay. So, we have now more or less completely constructed what is called the character table for C2v. There is something else that you will see in character tables, that is Rx, Ry, Rz. For now I am leaving that aside because we won't really use that too much in this course. That Rx, Ry, Rz just means rotation with respect to x or y or z. Yes sir. Not here, that will come later. You will see z square or x square will not go there directly. So here z square minus x square will belong to the same place, but here we do not need to invoke that, because x square and z square directly belong to some irreducible representation. Fine. So we are almost done, almost but not quite. We better give names to these irreducible representations. We do not want to leave them as gamma 1, gamma 2 and all that. So, and the thing is, we do not have to make up our own nomenclature, somebody much bigger has already done it. But even before we go that, I want to make this point. Another name for irreducible representation is symmetry species, and I would like you to understand the meaning of the term symmetry species. See, you look at this character table, what is the information that you get? You get the information of how each of these bases behave with respect to each of the symmetry operations, right. So, take X, it is symmetric with respect to E, antisymmetric with respect to C2, symmetric with respect to sigma V, antisymmetric with respect to sigma V dashed. Is there any other symmetry operation left? E C2 sigma V dashed. Is there any other symmetry operation left for this point group? No, right. So, what we have done essentially is that if you just look at this line, the irreducible representation, you will know exactly the complete behavior of each of the bases with respect to each and every symmetry operation. Okay. So, that is what tells you about the symmetry behavior, that is why these are called symmetry species. Each irreducible representation is called a symmetry species. Make sense? Okay. In fact, I like symmetry species better than irreducible representations. If you approach it from a mathematical point of view like what we have done, then irreducible representation makes sense. If you approach it more from a chemistry point of view, symmetry species is much more appealing. Fine. Now let us go ahead and give the names, and the system has been worked out by Mulligan long ago, and this is what it is. For one dimensional representations, the names that are given are either A or B, very systematic nomenclature, okay, either A or B. When is it A, when is it B, it is not left to you. You look at the characters. One dimensional representation, right. So, characters can be either +1 or -1, that is the advantage. Now look at, if there is a principal axis of symmetry, then look at the principal axis of symmetry. What are the characters? If the character is +1, then you call the symmetry species A. If the character is -1, then you call it B. Alright. That is why looking at the character of the principal axis of rotation. Now let us see here. So, gamma 1, is it A or B? A. Gamma 2, A. Gamma 3, B. Gamma 4, B. So, we have done some classification already, but it is not enough obviously, because you have 2 A's and 2 B's. How will I know which A is which? How will I know which B is which? So, we need a second level of identification. Mehak, you with me? From where?
Assignment of A and B.
Okay. So, believe me when I say that if it is one dimensional, we will call it either A or B, but that you better believe. Now, what I am saying is this: to determine whether an irreducible representation is A or B, what we do is we look up the character table and see what is the character for the principal axis of rotation. That is going to be either +1 or -1. See, here for gamma 1 and gamma 2, the character is +1, gamma 3 and gamma 4 character is -1. So, if it is +1, you call it A, if it is -1, then you call it B. So, these first two IRs are A, and third and fourth are B. But then A and B are obviously not enough. You have to call it A1, A2, B1, B2, something like that, isn't it? Big A, small a, whatever. So, we need a second level of nomenclature. Okay. And the second level is provided by, of course, What is next? Sigma v. E is hopeless in this matter, right? There is nothing whose character is anything other than 1 in this case. Can the character of E be anything other than 1 ever? Not in this case. But what happens if you have a 2-dimensional irreducible representation? Then the character is 2, character of E, isn't it? Then you cannot call it A or B. You don't even call it C or D, you call it E. Okay? And then what if it is 3? Then it is called T. T for 3. Okay? So that letter will change. No. But in this case what we do is A and B are defined, fine, you need a subscript or superscript or something. We start with a subscript. So you look at what is next. Suppose you have C2 axis perpendicular to the principal axis of symmetry. Or suppose you have vertical plane, any one of these two. If you have both, then you go by the perpendicular C2 axis first. That is the order of priority. Do you have perpendicular C2 axis here? No. Do you have sigma v? Yes. Which one do you go by? You go by the one that you have written first. Alright? You go by the one that you have written first. Fine. So then next is very simple. If that character is +1, then there is no point in writing another letter. You write a number, you use a subscript of 1, and if it is -1, then you use a subscript of 2. Simple. Now see, these two are A's, gamma 1 is A, gamma 2 is also A. So chi of sigma v here is +1, chi of sigma v here is -1. So this is A1, this is A2, and that is why. You ask, right, why I have written that first? Because it is A1. So I am writing it in some particular order, that is all. Are we all okay with this? Very simple. Okay. To the principal axis of symmetry, which is not there. Then it would have been not C2v, but something like D2 something. Okay. So now we know what the names are: A1, A2, B1, B2. Now the character table is complete except for that Rx and Ry. At least nomenclature is complete. Alright. Now the thing is, there is no guarantee that all irreducible representations have to be one-dimensional. We are going to see some example of two-dimensional irreducible representation today itself. Alright. So what happens if it is 2D? It is E. What happens if it is 3D? It is T. That is one point. Actually that should come later. But even before that, the issue is these are not the only symmetry elements, right? You can have a sigma h, right? If you have sigma h, this is what you do. If the character of sigma h is +1, then you use, now instead of subscript you use a superscript, you use prime, and if it is -1 you use double prime. These are very simple rules that we unfortunately have to remember, x double prime. And then you could also have inversion, center of inversion. So if the symmetry species is symmetric with respect to inversion, symmetric means what is the character? We are only talking about one-dimensional representation so far. What is the character if it is symmetric? 1. Then you call it G. Then you use a second subscript of G. What is the meaning of G? Gram Gerede. Gerede means symmetric. And opposite of G is U, ungerede, not symmetric, antisymmetric actually. Okay. So now see, everybody knows about those two sets of d orbitals, T2g and EG. Where did the names come from? The names came from here, the Mulliken nomenclature. EG, what are the d orbitals in EG? Z square, x square minus y square, right. They belong to EG. That is because when you look at the character table, right, of OH octahedron, you see that there is a symmetry species that is 2-dimensional and the name is Eg. That is where your those two d orbitals will belong. And T2g is another 3-dimensional symmetry species, 3-dimensional irreducible representation in the OH group. That is where the other 3 d orbitals belong. That is where the name has come from, Eg and T2g. Okay. When you talk about an octahedral, tetrahedral complex, for example, do you call them Eg and T2g anymore? What do you call them? Because the question of G or U does not arise anymore. There is no center of inversion. Okay. So the name, those names actually come from here. Okay. E, T, what we are talking about, all comes from here. And we will have a chance to talk about those as well little later on.